So a couple of announcements. The main announcement is really, and all the others are sub-bullets, is that you have a midterm on Monday. Study for that. There's a midterm prep page. There are extra office hours. There's a practice midterm. There is Piazza. There are many past midterms and exams that you can look at. Take advantage of all of that and try to do as well as possible. You know we like to make them hard, so you brace yourself to be prepared for a difficult midterm. All right, so kernels and clustering, topic for today. We're going to see a new type of machine learning today in terms of how the system will be learning, and the common thread throughout what we'll look at is this case-based learning idea. Think of it as, once you see one example of a certain image, let's say of a 3, then can you maybe, by comparing new images to the image you already saw, decide what that new image is? Is it also a 3, or is it maybe a different thing? Right. So the reason we'll be interested in this is because it'll give us a way to get richer classifiers than the ones we've looked at so far. And I'm saying that now, but then at the very end we'll see like, oh wait, actually we can combine what we saw in last lecture, what we're doing in this lecture, to get the best of both worlds in one. But for now, let's just look at this problem over here. If we have non-separable data, maybe end up with a decision boundary that looks like this, might be reasonable. And maybe you're happy with this. Maybe you say, well, probably this plus was noise and probably this negative was maybe noise too, and then we got the right decision boundary. But that's not necessarily true. What if you know your labels are all correct, for example? Then you now know that you're guaranteed to be making mistakes. You're not capturing the pattern, right? Because this line just can't separate the points. Okay, so in case-based reasoning, we do classification in a somewhat different way. The idea here is to predict the class label by finding the most similar instances in the training data and then transferring the label over from those most similar instances. So the simplest case is one nearest neighbor. One nearest neighbor means that you look at your current example, you find the closest match in your training data, you look at the label that training example had, and just use that label to predict the label for the current example. So that's shown in action over here. We have a positive here, and a negative here. The green zone is the zone where, of all points that are closest to the negative example, the white zone is a set of all points closest to a positive example, and that's now our classification boundary here, shown over here. A little pixelated, but that's the decision boundary. All right, so we get something different than a line here. It can be quite rich, actually, what you end up with. Now you might say, well, what if it's a noisy label? Then we transfer over the wrong thing. Well, if it's really noisy and you have enough data to kind of counter that noise, you could do that. So if you look at a scheme, rather than looking at the one nearest neighbor, you look at the k nearest neighbors, let's say 3 nearest neighbors, then you can take a majority vote. Whichever is the majority label among those 3 is what you're going to pick for your current example. K can be larger. If you have a lot of noise, you might want k to be large such that you can let things average out the right way for you. If you don't have any noise at all, then one nearest neighbor can be enough. So the key issue here is that we want to somehow measure similarity between training examples and then new examples. So such that this is a meaningful similarity. If we say this is the most similar one, that actually means the label will transfer over correctly. Right, so this is the first example of what is called a non-parametric approach to machine learning. So parametric, which we've looked at so far, means that you have a fixed set of parameters as you start out, and as you get data, you estimate those parameters. And the more data you get, the more accurate you're able to estimate those parameters. Naive Bayes was an example. You had a set of parameters, namely the conditional probabilities. The more data you got, the more accurately you could estimate those parameters. The thing is, once you've had a certain amount of data, your parameters will have converged in some sense. They won't change much anymore with even more data, and your decision boundary will be whatever it is. It might still make mistakes because you only have so many parameters to estimate, and it's not all that rich necessarily what you're able to represent as decision boundary. Non-parametric approaches, they will have a way to increase the complexity of the classifier with the amount of data. So nearest neighbor is an example. The more data points you have, the more complex your decision boundary could become. So let's take a look at this. Here is at the bottom, nearest neighbor example with just 2 examples. You actually get a linear classifier. Right? It's the line that's equally distant from both points, separating both classes now. You get more examples, 10 examples. Here you get a pretty complicated shape. Right? Get more data, you get an even more kind of rugged decision boundary here. Then if you have a ton of examples where you populate pretty much the entire space, you actually start fully seeing the pattern, and it might actually simplify again in this case. But the main point here is that as you get more examples, you're able to fine-tune in and refine what you decide your decision boundary to be. And if you get yet another example, it can yet fine-tune that decision boundary. Typically, this nearest neighbor type approaches or non-parametric approaches will start work better the more data you have. If you have very little data, they might not do all that well. Look at this case over here. We had 2 examples, and decision boundary is quite different from what we really wanted. Even for 10, it wasn't all that good a match and so forth. Of course, if you had something parametric and it's a line, you're not going to do all that well on this data anyway. If you get a lot of data, you'll find the best line to separate the 2 classes, and that best line will just not be that good. All right, so we can apply this nearest neighbor classification for digit classification. So what do we have here? We have a bunch of training examples. We have a test example, and we want to classify the test example. Well, what do? We might encode that test example again in a feature vector, which in this case could be a tuple of intensities. Then we need to find whatever is the most similar example in the training data set, right? So when we need to somehow compute similarity, here's one way to compute that. This is saying I'm computing the inner product between the feature vector that I had for my training example and my new example. The higher the inner product, the more similar they are. This is exactly like nearest neighbors. So let me show a little derivation here. If you were interested in finding the distance between 2 feature vectors, in this case x and x prime, you could compute that by the inner product between x minus x prime with itself. This is equal to x times x plus x prime times x prime minus 2x times x prime. Often what we'll do is we'll normalize feature vectors to put them all on the same scale. It's a very common thing to do. Once you have normalized the feature vectors, this is 1, this is 1. So this doesn't really affect the distance at all. Distance is really affected by x times x prime. The lower x times x prime, the larger the distance. And so distance is the opposite of similarity here. And measuring this thing here is really the same as measuring this thing over here. With distance, you want it to be as low as possible. With similarity, you want it to be as high as possible. For what we'll be looking at, similarity is much more useful. But keep in mind that effectively they're equivalent. But mathematically, similarity is a thing we'll be working with. Yes? Okay, so a couple of things here. First observation was that this seems a bad similarity metric. And I fully agree. This is very naive. This is just to illustrate the point. This is not the one you should be using if you really were doing digit classification. Although if you had infinite amounts of data, it would still start working at some point. Really, you'd want to use something a little more fancy. We'll get to that. To your point of what happens if you have a blank image and so forth, how does that all play out? Typically what you would do, if you get data, first thing you do is to do something called normalizing it or whitening it. What you do there is for every feature in your feature vector, you compute the average value and the standard deviation. And then you subtract out the average value, divide by the standard deviation, and that way all your features live on the same scale. And that will undo some of the issues you were talking about, but still, it's not a great feature vector. We'll get better ones soon. Yes?
So it's trying to find the one that has the maximum dot product?
Correct. So you would cycle through all of these, see which one is the highest dot product, check that label, and assign that label. That would be one nearest neighbor classification.
But like neighbors is a lot, right? But like you don't want something to
Okay, so if let's say something that's white has 0 and something completely black is 1, right? Then what you're getting at is that if an image is completely black, it'll be very similar with everything, right? So that is true. But what will happen if you normalize things, that image that is completely black will actually not be completely black anymore. Because every pixel is black. After you normalize, instead of being all ones, it'll become all ones divided by the number of pixels, so to say. And so the actual score will actually be pretty low. And in general, that in image classification or anything with images, contrast normalization tends to be pretty important. So you definitely want to do that. Absolutely. All right, so we're all pretty unhappy with the similarity function we saw so far. So let's start improving them. Rather than using the raw input and taking the inner product between x and x prime, use some feature representation. And then you'd have the inner product between the feature vectors f of x and f of x prime. Very special case is to just let f be the identity function, keep x. But in general, you'd want something a little more interesting. Okay. In addition, what you can try to do is make your metric somewhat invariant to whatever might happen, right? So here are things you might want to be invariant to. So what if things get rotated a little bit, translated a little bit, scaled a little bit, the stroke thickness changes? Those are the kind of things that you know don't change the label you should assign. It just changes the appearance of the digit, but not the actual number that it's representing. So you want some similarity metric that makes, whenever those transformations happen, two things that are transformed that way relative to each other have a high similarity score. So one way to do that is to explicitly change the way you score things. So rather than computing a similarity score between two images directly, you would compute a bunch of variants of each one of them. So you start with an image, you compute a bunch of variants that are the transformations you think are reasonable and keep things the same. And then when you compute similarity, instead of comparing two images, you have a set of images and a set of images. And between these two sets, you find the pair that matches the best. The similarity of that pair is the similarity score you use for those two examples. That's one way to go. Another way people sometimes go is to, rather than changing the similarity metric, is to just infuse more training data. So you would go through your training data, and you would make all those transformations, and you just say that makes for new training data of things of the same label that the original thing was. Then your data set is larger. You have a larger data set, but your algorithm remains simpler in terms of computing similarity. It's a trade-off. What's shown here is where you actually do more work at similarity computation, but keep a smaller training set. Either way works essentially equivalently. Okay, here's another trick you can play. You can say, well, if I'm going to measure similarity, what I want to do is understand what really a digit is. So you build a model. Let's say a 6 is shown over here. You have a model that consists of a bunch of edges, and you say that that template can be deformed. You can rotate these things, wiggle them a little bit around, and this might here give you the range of pixels that tend to get activated if you wiggle things around. And so as you get a new digit, you kind of see where the pixels are dark, then see if you can get your original 6 template to be reshaped to fall in the dark region without having to transform it too much. You measure how much you need to reshape your 6, your template 6, to fit it onto the dark part of the image. and then your similarity measure is based on how much you need to reshape things. You do the same thing for your template 8, 7, 9, and so forth, and see which one requires the least deformation to fit onto the dark part of the image. And then that gives you the similarity score with your template in this case. Okay, so as I mentioned earlier, at some point, 2 lectures from now, we'll see a way to also learn features, but in practice, a lot of the work in machine learning is to design the features yourself, come up with good features. We saw a couple of examples here. It often takes a lot of practice to get good at finding good features. What we want to do now is take a step back and say that really we've seen 2 stories so far. We've seen the kind of parametric approach. You have a set of parameters that you try to fit based on data. Naive-based perceptron do that. And we have seen the non-parametric story, where we come up with some similarity measure between examples and then use some kind of nearest neighbor approach to make decisions. At this point, each has their pro and con. The parametric approach, it's nice in the less data regime, right? Because you're just estimating some parameters and you can often do that from a relatively small amount of data. The non-parametric approach might take more data, but then it's more flexible. As you get more data, you can adapt. What the non-parametric approach is not doing is zoning in on where your decisions should be made. In the parametric approach, perceptron zones in on the decision boundary, tries to position it really accurately. The nearest neighbor approach doesn't even have a notion of decision boundary really. There's no training happening. You just store your training data and then look things up. And there's no adjustments happening based on your training data to get the decision boundary in the right spot. What we'll look at now is a way to fuse those 2 approaches. So we in some sense get the benefit of nearest neighbor, the non-parametric representation, yet at the same time we still get the perceptron characteristic of being able to zone in on where the decision boundary should be. Okay, let's see if we can get both working at once. This is called kernelization, what we'll be doing. So let's revisit perceptron. So a weight vector wy for a specific class label y, what does it look like? Remember the perceptron updates. When does wy get changed? If you predict y incorrectly, then we'll subtract f of x from wy. If we predict y, we should predict y, but we didn't, then we add f of x to wy. So all updates to wy are of the form wy plus f of x or negative f of x. And then we'll go to the next example. Sometimes there's no update. So this is a very particular form. We see that wy will always be of this kind of format. This is the key observation. So every vector wy can be written as a weighted combination of feature vectors that are computed on the training data. These values here that you have, the alpha iy stands for a weight where the I indexes into training examples. So it's a weight of training example xi, to which extent it contributes to weight vector wy. From what we know here, we know these alpha iys will all be integers. They all start out as 0. And then when you see a training example I, it might become +1, -1, it might stay 0, and you keep going. And then at some point it might become +2 if it already was +1 and another one was added and so forth. Okay, what we're going to do now is rather than keeping track of the weight vectors, which we've done so far, we're going to keep track of these alpha quantities. Think of as dual variables, dual weight vectors. If we keep track during the perceptron updates of these alpha quantities, we can always still reconstruct the weight vector. All we have to do to find wy is do this computation over here. So we still have the same information, it's just a different way of keeping track of it. Okay. Alpha iy is defined as if you run a perceptron algorithm and you keep track of how much f of xi contributes to the weight wy, alpha iy is that number that tells you how much it has contributed. Initial will be 0, then it might increase or decrease over time. So this here defines what it means. So let's look at the algorithm in action. keeping track of these dual variables. So we get a new example. We see what the current set of weights would give as its classification. So wi times f of x, which now we compute this way over here because we're not keeping track of the wi's anymore, just of the alpha quantities. So we have to compute our weight vector this way, and then we can inner product it with f of x to see how high y scores. Okay, now what we do is we reorganize this computation. F of x doesn't vary with the index I here. So sum over I, we can bring that in. We brought in f of x right in here. Still the same quantity we're computing with, just a different way of computing the same thing. Okay? Now we're replacing this inner product between f of xi and f of x with k xi comma x. K is a function that takes in two training examples and outputs the inner product f of xi times f of x. Okay? So what we have now is that as we want to evaluate a new training example, what we do is we compute the similarity k between xi and x for each example xi we've seen so far that's participating in the weight vector. And then once we computed all these quantities, we sum them together with their appropriate weights, and that gives us a decision, a score for y. So the score for y here can be computed without ever actually accessing wy. We got rid of wy in some way. Instead now we have this computation over here. Now once you have this format, you could argue, and we will argue, that, hey, we keep track of these alpha iys. All we're using now is the similarity function k. We don't need the original features anymore. We can use any similarity function, and there is some fine print we'll get to later, but you could use this now with any similarity function. However way you compute similarity between xi and x, you can then fill in that similarity over here as your result, compute a score for classification label y. Okay, so dual perceptron looks like this. You start with all alphas equal to 0. Then we pick up training examples one by one, try to classify your current training example xn. You look at the score you get for each possible label y, which can be computed this way. We have access to a similarity function and then these alphas that we compute during this algorithm. If it's correct, nothing has to change, no update. If it's wrong, normally we would do this update over here, but we don't have the weight vector w lying around. The equivalent thing to do is to perform the update on the left, an update to alpha yn, and an update to alpha y star n. Yes?
But the alphas, you're continuing updating. It's not like it's
Yes, so you would have, in some sense you would have for each label, let's say there was a label y1, y2, y3, you would have an alpha vector sitting here with entries 1, 2, and so forth, till k, if k is the number of training examples you have. This would be your alpha 1 y1, alpha 2 y1, alpha k y1. And you'd have another one here and another one here. So you'd have, in some sense, a two-dimensional array of weights that you're keeping track of.
Are they just 1, 0, or negative 1?
Initially, they're all 0. As you loop through your training examples, they can increase by 1 or decrease by 1, but can happen more than once. So one of them could be increased multiple times or decreased multiple times. So it could also end up being +2, +3, and so forth. And so this here, this axis would be the number of classes, number of different labels there are, and this axis here is the number of training examples. I guess I shouldn't have used k here for number of training examples. Let's call it capital N. Then this summation here, I, would go from 1 through n, which is the number of training examples. Yes, summation goes like this. Correct, yeah. So, but this is how it works out. One way to know how things work out is to look at the indices. If you're worried about ambiguity, there's an I here, so there's a summation over I. So everything that has an I here is implied to be part of that summation. Otherwise, it doesn't make sense to have that I later on. All right, so that's a dual perceptron. We call it the kernelized perceptron. And the reason we call it kernelized perceptron is because this function here, the similarity function, is often called a kernel function. That kernel function, the fact that we can substitute this in instead of regular features is called the kernel trick. Any algorithm where you were to learn a weight vector that's multiplied with a feature vector, and if somehow you can show that as you execute your algorithm, your weight vector will be a weighted sum of training example feature vectors, any of those situations, you can apply the kernel trick and then work in the dual space. Right, so keep in mind, the key reason we were able to do this is because we knew Wy would be some weighted sum of training example feature vectors. We knew that was going to be true by analyzing the algorithm. And so we knew that when we made this decision here, computing that score, that if we substitute this in, we effectively can bring this f of x together with this f of xi here, and we get the inner product between the two feature vectors and then the alpha coefficients. And that inner product sitting right here, f of xi times f of x. Okay? Now that we've shown that this is possible, it also turns out that we can now sometimes forget about it and say, well, whenever we have a similarity function, we can run the perceptron algorithm with the similarity function. We'd be running the kernelized perceptron and do exactly what you saw on the previous slide. Okay. The kernel is a function just in this very similar way that the feature thing is a function. You compute a feature from your input. So you have a function f that takes your input, computes a feature vector. Similarly, your kernel function will take two examples, compute a similarity between them. For the math we do, we don't need to know what that is. Just like for the math we do here, we don't need to know what f is exactly doing. If you want to implement anything, you actually need to know what k is doing. You need to know what f is doing. If you use the primal perceptron, you need to know what f is doing. If you use the dual perceptron, you need to know what you need to put inside k, because you need to write a piece of code that actually computes that k. Okay, so why do we care? The simplest way to think of it is that we just replace the inner product between f of xi and f of x with a new function, kxi, x. And in principle, your code for k could be compute feature vector f of x, compute feature vector f of xi, inner product them. That'd be a valid kernel. Then there would be no use of this kernel trick. You'd be back to doing whatever you were already doing before. The power of this trick is that you don't need inside your kernel function to be computing explicitly two feature vectors and inner product in them. You can compute any similarity with some fine print inside that kernel function. And that's why it's interesting. What's the fine print? There are some technical requirements. If they're not satisfied, some proofs will break. Essentially, the technical requirement comes down that there exists some feature vector such that indeed your kernel is the inner product between feature vector on the first example and feature vector on the second example. But you don't need to compute it that way. And often you can bypass computing the feature vectors and compute similarities where the feature vector that actually exists is infinitely long. So you would stand no chance working with a feature vector, because an infinitely long feature vector would take too long to compute. But the kernel can still be computed very quickly. Okay, so this allows us to have richer hypotheses. We will not be restricted to this kind of linear classifiers that we've seen before, right? We now have non-linearity effectively. So here's an example of what's going on underneath. Let's say you wanted to make a decision. Things were, in this case, linearly separable. Sure, no problem. You can classify things, works out. But what if the data set's too hard? This is not linearly separable here. What you can do is you can augment your space. This is computing extra features from your original feature set, so to say. You start with just one feature, x. You included an extra feature, x squared. And now, all of a sudden, things are separable. So this is a neat little trick where you say, hey, by including more features, things become separable. We'll ask you questions like that. What extra features will make this data set separable? Such that in the higher dimensional space, you can actually classify things. So this is nice. You can definitely do this. Often what you want to do is add a lot of features. If you have a lot of data, you can allow yourself a lot of features. And this might become a very high dimensional space, but then you have a high chance of being able to separate things properly. So here's another example. You start two-dimensional. You see that one class lies in the inner part of the plane, the other class on the outer part. You introduce an extra feature, which is the distance from the origin. Now in 3D, you can separate linearly the red from the blue class. This is a game you'll often end up playing. Okay, so here's why kernels could be really handy to get the kind of same effect in a more efficient way. The simplest kernel is the linear kernel, which just computes the inner product between its inputs. Here's a different kernel, the quadratic kernel. It's computing the inner product between its inputs, then adding one, and then squaring that quantity. You can work this out and show this is equal to this expression over here. What is this expression? Well, this is also an inner product, because this comes from x prime, this comes from x prime, and then this comes from x, this comes from x. So what's going on here is we're computing an inner product between two feature vectors that look as follows. We have 1, x1, x2. Let's go just up to 2. Then x1, x2. And we have 1, x1 prime, x2 prime, and x1 prime, x2 prime. Take the inner product between those two. The 1 and the 1 ends up over here. I guess we need a square root 2 here to make this work out. So put a square root 2 over here. Now we have these terms covered, and then these terms are only one of them in this case, which will be these two multiplied together in the bottom row. So what I just showed you is that this quadratic kernel corresponds to a particular feature vector, f of x, that looks as follows. This was for a two-dimensional x. The input was just two-dimensional x1, x2. This would still be true if you had a higher dimensional input vector. If your input vector was, let's say, 100-dimensional, you could still compute this feature vector where you have an entry of 1, then an entry for each original feature, and then an entry for each possible pair of the original features. At that point, when you look at each possible pair of original features, that would be 100 choose 2, which is roughly 100 squared. So you have roughly 10,000 features. You could compute that feature vector, which would have 10,000 features in it, for both examples, inner product them, sum together, and see what you get. Alternatively, you could work in the original space here, just do x times x prime in the original space, which just has about 100 entries, not 10,000. Much cheaper inner product here, x times x prime, add 1, square it, and get the same quantity. So what you see here is that this calculation over here is much cheaper than the second version. The first version is the kernelized version. It's where you directly compute the kernel quantity. The second version is the one where you first go to this high-dimensional feature space and then compute the inner product in the high-dimensional feature space. What's interesting here is that these are two ways of looking at the same thing. And this allows you to interpret what's going on if you were to run, let's say, the kernelized perceptron with the quadratic kernel, which is this kernel over here. You know that's equivalent to running the original perceptron in this higher dimensional feature space. So effectively, by using this quadratic kernel, you're lifting everything into a much higher dimensional space, where you have a higher chance, of course, of being able to separate things linearly because you have many more ways to slice through your data. And so what's effectively happening using this kernel is working in this much higher dimensional space where now things might be linearly separable. Of course, if you look in the original space, whatever looks linear in this high-dimensional space will look nonlinear in the original space, right? So in the original space, you'll have some nonlinear decision boundary going through your original space, which corresponds to this linear decision boundary in the high-dimensional space. Here's another example. The Gaussian or radial basis function kernel. This is computing the distance between x and x prime, squares it, takes a negative it, and then exponentiates it. So this will be high if the 2 points are close together, and very close to 0 if the points are far apart. There is, again, a feature vector that corresponds to this kernel. Happens to be infinite dimensional. We can't put it on the slide, but there's an infinite dimensional feature vector that we don't have on the slide that corresponds to this kernel. What that means is if you run the perceptron algorithm with this kernel, you're effectively working in an infinite dimensional space. In that infinite dimensional space, pretty good chance you can find a separator, of course, between your two classes, because so many dimensions, so many directions to slice your data. That separator in your low-dimensional original space will not look linear anymore, because in your low-dimensional space, everything's been collapsed. And you actually, if you use this particular kernel, the exponential kernel, you get something that looks a lot like nearest neighbors, because you'll essentially get a nearest neighbor classifier here. This will give you a nearest neighbor classifier, because if you look at what's going on, the way you make decisions is going to be some weighted sum of similarities. And for this kind of kernel, only very close things will have a similarity that matters. Once you're far away, exponential decays very quickly. You get essentially 0. So what contributes in this sum over here will only be the data points that are very close to your point x. So only xi close to x will have a non-zero value here, and then that non-zero value will be weighted in some way. In nearest neighbor, where we just weight the one that's closest, we'd be done. In the kernelized perceptron, our training algorithm fine-tunes how to weight each one of these data points to do better than what the nearest neighbor would have done naively. So you get, in some sense, a trained nearest neighbor-like classifier, same expressiveness, but trained to get the decisions as well as possible on the training data. Yes, Patrick? True. You can show, there's something called VC dimension. And what that says, it looks at, as a function of the dimensionality of the space, how many data points are you guaranteed to be able to separate in any possible way. So for example, in, let's say, n dimensions, you can show that if you have n data points, you can always separate them, no matter how you label your training data. For example, in 2 dimensions, you have 2 training data points, you can always separate them and get your classes correct, no matter which one you call positive, which one you call negative. In 3 dimensions with 3, you can always succeed, no matter how people label them, you can always find a separator, and so forth. What that does mean is that if you only have n training examples, going to n-dimensional space is a pretty bad idea, because whatever people came up with their labels, you're going to be able to fit, so you're very susceptible to noise. So you need to be careful about that. You need to have holdout data that will tell you to how high dimensional space you're willing to go. So you have holdout data, you use it for cross-validation, so you don't expand your feature space too much, and then somehow don't generalize well. And there was another question here.
For the original question of how companies also
Correct. So how do we tell similarity in the nearest neighbor space? Different k functions will measure similarity in different ways. So in practice, you could do 2 things. One thing you could do is to just come up with a bunch of k's, different functions, use some holdout data to see which k function performs better on the holdout data, pick that one. Sometimes there's a continuous parameter. So sometimes what you can do is you can have, let's say, a scaling parameter here, divide by some sigma squared, let's say, which kind of rescales of what distance you're willing to look. Then you could even do a hill climbing procedure. You could say, as I perturb sigma squared a little bit, do I do better or worse? If I do better, I keep it, and you could fine-tune your choice of parameter. So if it's a parameter that's a continuous thing to tweak, you'd probably do hill climbing. If it's a discrete set of choices, you'd compare how they perform.
So when you're offline testing and for online.
Correct. So I think this is worth kind of reiterating because it's maybe the most important concept in machine learning of all concepts is that when you get your data, you will split into three, so to say. Right? You'll have training data, holdout data, and then it will be test data, which is kind of what's there for the future. The training data is what you use to estimate the bulk of your parameters. So in this case, you would estimate on the training data your alpha parameters. For the primal perceptron on the training data, you'd estimate your W. For naive Bayes, you'd estimate your conditional probabilities on the training data. Then there are some hyperparameters, some extra parameters you have, right? So you don't know maybe what kernel to use. You don't know what K for Laplace smoothing to use. For the primal perceptron, maybe you don't know which feature vector to use. Those are your hyperparameters. So you will run training for each possible setting of your hyperparameters, then test on the holdout data which setting of the hyperparameters ended up doing best on the holdout data, and then that is how you select which hyperparameter setting to choose. So maybe you say, oh, I should use dual perceptron with this particular Gaussian kernel with sigma equals 0.5. Then normally what you would do is you would grab both your training data and your holdout data, retrain your alpha parameters with all that data, and now you're done with full training. And that would hopefully do best on your test data that you haven't ever seen before.
It seems like in one step, you're adjusting the output, and then the second step, you're adjusting the phase. But like, couldn't it be that it should be like try to do the right approach because you would have to like iterate maybe like the one that worked best for this output.
Okay, so when I say you select hyperparameters, let's say you select a kernel function K, the way you select between two kernel functions is by first for each one of those kernel functions, you do a full training run. So for kernel function 1, you run your dual perceptron until converged. Then for kernel function 2, you run your dual perceptron until converged. Then for each of those fully trained dual perceptrons, you compute the accuracy on the holdout data. You compare their accuracies. So each of them will already have been fully trained. You compare the accuracies on the fully trained versions of each one of them, and then pick the one that did best. Yes? It is. So holdout data is a way to kind of gauge how well you think you'll do on the test data. Sometimes something a little subtle going on in that you need to be careful, of course. Once you start evaluating too many things on your holdout data, it's not going to be representative anymore of how well you're doing your test data. That's why the kind of rule of thumb is that the bulk of the parameters you fit with your training data, and then only the hyperparameters, the kind of small set of remaining choices, is what you select. You select the hyperparameters based on your holdout data. So then, of course, it's kind of a subtle game there. When is it a hyperparameter? When is it a normal parameter? And so forth. Usually it's pretty clear which are the normal parameters, which are the hyperparameters. But of course, it's a pretty fuzzy line. You can come up with cases where, it could be a hard call to decide which one is the training parameter, which is the hyperparameter, right? You could say, well, should this sigma thing here be a hyperparameter or a training parameter? Not entirely clear. Yeah, typical choice would be 70% train, 30% holdout. So test data, in reality, the test data is what you don't even know exists. It's whatever is out there in the real world, right? In a lot of research settings, the test data is dedicated data that's used to compare machine learning approaches. So somebody holds back the test data somewhere in some repository. You do your training using the data you have, which is split into train and holdout, and the test data would be sitting somewhere else. And once you're done fully training and validating, you send off your classifier, and hopefully you rank high in whatever competition they're holding. Yes?
So is there situations where the RP actually gets that place, like where it's problematic to go higher
Absolutely. So in some sense, what you want to do is you want to encode some prior information of what you know about your data into these kernels. And the RBF is encoding very limited prior information, right? It's just saying whatever is closed is probably going to have a similar label. But it might be that if you're closed on feature 1, that's very representative of having the same label, but being closed on feature 2 has nothing to do with the fact that you should have the same label and so forth. And so this kind of kernel will not be very well attuned to that kind of situation. Yeah, it makes very few assumptions, so you might need a lot of data before you get things right. But the thing is, in the limit, you will start getting things right, because this is like a nearest neighbor, right, where you get to tune how you vote. Nearest neighbor voted in a set way. The nearest ones are the ones that vote. You say how many you're willing to look at, then you vote. Here, you have a weighted way of voting based on distance, but it's mostly the ones that are really nearby that actually contribute, and then weighted based on however the training told you should be weighting certain examples. So in this case here, right, if you had a noisy example, if you had all positives, so to say, and it was a negative in there, right, then that negative here would probably end up with a 0 weight, such that it wouldn't contribute, because the training process would understand that that's a noisy example, and it can weight it down to 0, whereas nearest neighbors doesn't have that mechanism. So in this sense, this is better. Of course, you pay a price. You have to do the training ahead of time before you then can do classification. Okay, so I think we discussed this quite a bit in detail, but let's just recap here. Why do we care about kernels? Right. What's the whole idea here? Why not just work in feature space directly? In principle, you could work in feature space. But in practice, it's not always as efficient. We saw the quadratic kernel example, where computing the kernel value between x and x prime is much more efficient than first going to feature space and then computing the inner product. For some of them, like the Gaussian kernel, that feature vector is very, very large, and it'd be completely impractical. Sometimes also that infinite feature vector might not be as intuitive. The Gaussian kernel is very intuitive. You essentially have a region around the point where it can have influence, and away from that region, it can't influence things. If you look at the details, the Gaussian kernel actually, the features correspond to some kind of Fourier expansion of a Gaussian function, which is kind of not at all directly related to how classification works. Whereas the kernel itself is a very clear similarity measure. And so it often makes sense to reason directly in kernel space. So there are reasons to work in kernel space. Keep in mind that in principle, you can always think of it still as working in some feature space. So it gives you two ways of thinking about the same problem, right? This is something important to keep in mind. And the quadratic kernel is a good example there. If I ask you, well, is it likely to overfit, right? If I tell you, if you work in a n-dimensional space, then endpoints can always be classified correctly no matter how you label them. You can always separate things perfectly, so likely you're overfitting. If you have only n examples, you work in an n-dimensional space. If I now say, hey, we're working in an n-dimensional space, we'll use a Gaussian quadratic kernel, then you can say, well, quadratic kernel effectively lifts it to a n-squared dimensional space. So then definitely we're going to be overfitting even more. It's way worse than what we had before, most likely. All right, I don't think we can get through clustering in the remainder of this lecture. So what I'm going to do is I'm going to actually not take a break, continue for about 3 minutes, and then we'll stop for today. And we'll cut clustering off what you're supposed to study for the final. But the slides are there if you want to learn about it. But I just want to show you a quick picture of, so this is not going to be material to study, but I just want to show a quick picture of what clustering tends to do. The idea in clustering is that you get data, but it doesn't have labels. So you're not trying to find decision boundaries between your data that match up with labels. Rather, you're trying to explore your data. So here could be a data set. And one way of clustering is k-means clustering. And the idea is that you try to find representative centers for what you intuitively think of clusters in your data. So you can imagine that you think of this as a cluster, this is a cluster, this over here, this over here, this over here. Now keep in mind, in reality, this will be happening in some kind of 100,000 million dimensional space. You're not going to be able to just plot it and say, oh, I see my clusters. The reason you run clustering is because in a high dimensional space, this kind of effect of finding the regions where there is dense data can still work. What you can then do is you can pull up representative examples of each of these clusters and inspect that indeed these are very similar things. So if you fed in digits into a clustering algorithm, you'd hope that one cluster would have all the ones. There's no such guarantee because you didn't tell it that the ones are similar. But if somehow in the metric you're using, ones are similar, then one cluster could have all ones if you're lucky. So the way k-means works is as follows. You start with some centers. The red dots are the centers. They're not the right centers, they're just some initialization. Then you partition the space according to what's closest to each center. Everything over here is closest to the top center over here. Then all those points will gather that are in that region will gather with that cluster. After you have all those points collected, you take the average of all those points to compute a new center for that set of points. And here's the new center for each of these regions. And then you iterate. So very simple procedure. You start with some random centers. You take, for each point, you assign it to whatever center was closest. And then for each center, you now compute a new mean of all the points that were assigned to it. Keep iterating. So here's k-means in action on a 5 cluster problem. So you see, as the algorithm iterates, the centers move, the data assignment kind of shifts along, and in this case, we end up with a nice clustering. Is this guaranteed? No, there's no such guarantee. I'm going to take questions after we wrap up. So, but often it can work. Again, it'll depend a lot on the similarity metric you use, right? Because if you were to rescale these axes, rescale the horizontal axis by a factor 1,000, you'll end up with a very different clustering most likely. So keep in mind, again, very sensitive to whatever distance metric or similarity metric you use. So on the slides, it'll explain to you if you want to read in more detail. Also happy to tell more about it in office hours or on Piazza, that this procedure actually can be interpreted as an optimization procedure. And this is something, as you go along in machine learning, you'll see that a lot of procedures, rather than being thought of as just procedures, you'll think of them as optimizations. You're looking at how to optimize some objective. The reason that's nice is because it allows you to prove things like convergence. Because if you can prove your algorithm hill climbs on an objective function, and if your objective function is bounded, then it means at some point you'll be done. It also means that it sometimes is easy to understand what your algorithm will converge to. Because you have this objective, and you know, well, it's going to find a local minimum of this objective, so now I understand what it's doing. For k-means, it finds a set of centers that minimizes the average squared distance of each point to its closest center. Things can go wrong as you exchange kind of who gets what. Things can go right. You often have to reinitialize randomly and hope that you find a good local optimum at some point. So here are the updates, explain in a little more detail. Again, not something we'll ask you about. Initialization matters. This over here will get stuck. The red will continue to contain 4 points, and blue and green will each have 1 point. Again, multiple random initializations, just like you did with any kind of hill climbing, and hopefully you find a good one at some point. Okay? So you can get stuck. That's one type of clustering. Then I want to kind of give you a whole different idea, is the idea of agglomerative clustering. The idea there is that rather than having centers that move around, is you start with all your data points being their own cluster. So with 100 data points, you start with 100 clusters. And then you see which two are the closest together. You agglomerate them. Now you have one cluster that consists of 2 data points, and then all the other ones are their own cluster. Then you again look which two are the closest together, agglomerate them, and keep repeating. And so recursively, you build up some kind of tree structure of how things agglomerate, and it gives you a way to build a clustering at a different level of granularity depending on where you stop. So That's what agglomerative clustering looks like. Of course, there's different ways to combine clusters. Do you take the nearest point between two clusters that you already have, or the furthest point, or some average? It'll again affect what you get. Here's what I wanted to get to. Here's an example of clustering in action. So what is going on here? This is Google News, right? Any given day, there are a lot of news articles. Underneath what Google is doing, of course, they don't tell us exactly what they're doing, but we can take a hunch at it, right? Underneath what they're doing is they're running a clustering algorithm. They're looking at all these news articles. They're agglomerating them, or maybe k-means, whatever they're doing, to gather articles that are very similar. This is in a high-dimensional space. Essentially, each of these articles is some huge word vector, right? And somehow they're running clustering in that word vector space. Then, in this case, maybe they found 1, 2, 3, 4, 5, 6. These are 6 clusters being shown. And what's interesting here is that, and this will always be the case in clustering, you will have to somehow decide how to visualize your clusters. They didn't compute the mean of each of these clusters and showed us the mean. The mean would have been some feature vector with word counts. Not really interested in a feature vector of word counts. What it is, they've then said, well, let's pick something as representative as possible. Let's say you compute the mean and then find whatever article is closest to the mean. Grab that one and say that's representative of this cluster. You might use something else. You might prioritize, let's say, sources. Maybe you know you have a page rank over pages, and if it comes from New York Times, whatever is from the New York Times in a given cluster maybe is more likely to be displayed than something from a local newspaper. But that's what you're seeing here. The first is a bunch of articles that happen to be clustered that relate to heavy fighting continues as Pakistan, army battles Taliban. The words don't necessarily exactly match in all the headers and so forth, but somehow this clustering algorithm decided that these were similar. In general, clustering will happen a lot, or will need to happen a lot whenever you're exploring data, where you don't have very precise structure to your data that you're aware of, you don't have labels, but you still want to explore somehow what's in there, and often the next step is some visualization. This is a very basic visualization, but there are other visualizations out there that people have come up with on how to visualize these clusters. Okay, where are we at in 188 right now? Right now we have wrapped up everything. Well, right before we started clustering, we wrapped up everything we might quiz you about on any exam. Clustering is not going to be part of the exams. What we'll do in the next 3 lectures will also not be part of exams. The next 3 lectures we'll look at applications. We'll go back at things we've already seen, see how you can apply them in programming AI for computer games, in fact, StarCraft. We'll look at how you can apply it to natural language applications such as machine translation, Google search. We'll look at how you can recognize things in images, and we'll look at how you can get robots to do interesting things thanks to AI that you put into the robots. All right, good luck studying for the midterm.